Today, our SETI colloquium speaker is Anne-Marie Cody. Anne-Marie got her undergrad degree at Harvard, master's at Cambridge, and then a PhD in astronomy at Caltech, if I'm remembering all of that correctly. She's been working at NASA Ames through the NASA postdoc program and has just recently started running projects through SETI. She's worked on a wide range of projects involving variable stars, young stars, planet formation, and she'll be talking about some of that work today.
Testing. Okay, great. Thank you. So as I hope you'll hear today, we have a lot of very exciting science going on to do with star and planet formation and some new observations that are just coming in. The work that I'll be sharing with you would not have been possible without the help of numerous other scientists, some from my previous institution at Caltech, some from NASA Ames, and in particular the folks that work with the Kepler and K2 missions, as well as many people around the world. So I have been really amazed at all the planets that have been found in the past 15 or so years, and I'm sure many of you are very familiar with this, in particular all the planets that have been found via transits with the Kepler mission. And the full tally, you can see right here, includes thousands of planets. And the amazing thing is that if you extrapolate the statistics, there are probably billions of planets in our galaxy, so we're only seeing a small fraction. But that small fraction that we observe encompasses a great range of properties in both size on the left axis, going from sub-Earth to larger than Jupiter, and also orbital period, going from thousands of days down to less than 1 day orbital periods. This is an amazing range of properties, particularly in comparison to what we see in our own solar system. And what I find very interesting is the close-in planets. These were quite a big surprise when we first started finding planets around other stars. And most of them were found either via the radial velocity method, where we monitor the wobble of a star to see if there's a planet tugging on it, or the transit method, where the orbital plane of the planet is in our line of sight, and it causes the light from the star to appear to dim periodically as the planet goes by. And using mainly those two methods, but a few other methods as well, we have found hot Jupiters and super Earths, as they are known, orbiting at distances from their host stars that are about 1/10 of the Earth-Sun distance, 1 AU, at quite a variety of masses. And so most of the planets that have been found so far are around middle-aged stars, and so we infer that the planets themselves are sort of middle-aged planets. And one of the million-dollar questions which we have yet to answer is, how did all of those close-in planets get there? And that's what I'd like to specifically focus on today, how they formed. And none of these planets are being observed in their formation epoch. So it could be that they formed right near their host stars, and that's where they were born. Or it could be that they formed further out, and then they migrated inward via some process. And so really the only way to there are several ways to study how these planets got there, which I'll outline in a moment. So to put this in context, planet formation really happens as a part of the end stages of star formation. We begin with a molecular cloud, which then collapses down and forms more dense regions. And then eventually the angular momentum, the rotation of that material, forms a disk around the central star. And it is that disk material that eventually, we believe, gives rise to the planets around these stars. That material eventually disperses, and we may be left with a planet system. And so what I want to hone in on today is how these final stages of star formation and the beginning stages of planet formation, how we think they happen. So here's sort of a bit of an animation. I can get it to go. So we have these somewhat flat disks around stars with a lot of dust and gas. And then somehow, there are many theories about how this happens, clumps form. We get a bunch of protoplanets. And then those gravitationally interact with each other to produce the final configuration, which might be many planets, one planet, no planets. Some of them may go into the central star. So we have yet to observe anything like this directly. But there are now, I think, two main observational approaches to investigating planet formation, which are just starting to get going. And one of them is to look at the very young stars that still have that dusty disk material around them that may be forming planets right now, and to look for evidence that planets are forming in the disk through indirect signatures. So that's one way. And the other way is to look for planets themselves shortly before or after that disk material disperses, when it's not so thick that we can't see through it. And so I'll be telling you about progress that we're making on both those fronts today. So starting with the first one, looking at the disks themselves for indirect signatures of forming planets, there are sort of two ways to do that. There's imaging the disks, and then there are time domain studies where we actually look at how the material in the disk moves around the star, and we map that out with time. So there has been a lot of progress in disk imaging, and these are several stunning images which have come in the last couple years. The upper left is an image from the Subaru telescope, and what you see is the central star has been blocked out, and so you see actually spiral arms, which are the disk material around that star. And it's thought that that structure may be related to the presence of forming planets in the disk. There are also alternative theories for how a disk without planets could form that structure as well, so this is an active area of investigation. There have also been images in the millimeter wavelength by the ALMA interferometer, as you see on the lower right. And this is another spectacular image where there were lanes in the dust disks, which are thought to be related to forming planets in that disk, which we have yet to see. But again, there are some alternative theories for how these lanes could appear in the absence of planets. So as you can see, there's some very tantalizing evidence for observing the signatures of planets and disks, but we have yet to see the planets themselves. Now, the other issue with these imaging methods is that we can't see the very close-in regions. So I told you it's fascinating to think about how to get those very close-in planets that are closer to their stars than we are to the sun by quite a bit. And we don't have the spatial resolution to actually resolve those inner parts. So these images that I'm showing you now are hundreds of astronomical units. So they're actually informing us about how planets might form further out. So if we consider a schematic looking at a disk from the side, typically they have sort of a flared shape. The central star is in the middle here. There's a dusty region in the outer parts, and then the dust, where the dust ends, there's probably purely gas, and that inner dust rim is somewhere around 1/10 to 1 AU, the Earth-Sun distance. And as you might recall, that is where we're finding all these close-in planets. So somehow, not only are planets presumably forming further out, where you might expect Saturn and Jupiter in our own system, but they're also getting very close in. So there must be something really interesting going on in the regions of these protoplanetary disks. But unfortunately, we only have a few methods, mostly involving interferometry, that can look that close in, and they tend to only work around very bright stars. So with direct imaging or interferometry with facilities like ALMA that look in the millimeter, we're probing the outer regions, and so we can't get much more information about what's going on in here. So there's one interesting way to learn about what is happening in the innermost reaches of the disks, and that is using time series data where we look at the brightness of a star with a disk over time, and we can actually map out features in the inner disk that are orbiting around the star at a fairly close distance. And I'll show you how that is done. So all these young stars, when I say young, I mean a few million years old. That's what young is in astronomy. And we've actually known for about a century that stars of that age are highly variable. This is some data from the early 1900s that shows young stars varying at almost a 100% level. So you can imagine if the sun were a young star, which it's not, it's billions of years old, not millions of years old. If you went out tomorrow, the sun might be twice as bright or half as bright. So it's pretty spectacular. And we've known this for a while, but the thing is, data from ground-based telescopes is always pretty sparse. So you can see in this case, there were data points taken over many months, and you can see the variability, but you can't really infer anything else about it. So there's a couple reasons for that variability. Some of it is cool star spots. The young stars have strong magnetic fields in many cases, which creates big spots on their surface, much bigger than that of the sun. And they tend to cause roughly sinusoidal periodic variations in the starlight. So when we get a light curve, we tend to see that, and we can actually use that repetition to measure the speed of the star's rotation. So that's one thing that we see. And this is some examples of data from a few years ago showing the effects of the star spots on brightness. And these are light curves, the brightness of stars over time that have been phased up to the star's rotation period. And you see these kind of sinusoidal variations. They tend to have periods of about a day to a week and amplitudes of a few percent. And you can already start to see why it might be hard to find planets around these stars, because they're varying at a few percent level or more, and that's typically, if you want to look for planetary transits, about the level that you would be looking for the dimming in the light curve. Of course, you might be able to take the signal out, but it gets harder. So these young stars also have some other variability due to hot spots on the surface, and that is because gas from their protoplanetary disks funnels in along the magnetic field lines, hits the surface, and creates shocks, and then that puts out all kinds of visible and UV radiation. And we get flux variations such as this. This is a simulation, which are much more chaotic than those created by the cool star spots. And so, indeed, we also see many young stars with aperiodic variations. This data is over 2-week time scales, but longer time scale data also shows that they vary on long terms, short terms, pretty much any time scale you look at a young star that has a disk and material accreting off that disk, you will see variations on those time scales. And it ranges from anything from a few percent variation to over 100%. So that makes it extra hard to find planets around these objects. And then there is a further issue, which is that if you look at a star and it has a protoplanetary disk, which is aligned with our line of sight, you're going to be looking through that material. This is an artist's conception. Of course, we would love to take a picture like this, but we can't. We don't have those capabilities. You're actually looking through that material, and it's orbiting around the star. And so if you want to detect a planet forming in there, you've got all this other junk in the way. And in fact, the stars are partially blocked, and we can see the influence of this stuff going by. And we have some examples of young stars that have these interesting fading events. Some of them are kind of periodic, but they come and go. And again, they can influence the measured flux of the parent star by a few percent to 30% or even more. And so that makes it hard to find planets, but as I think you'll see in a moment, it actually does inform us about planet formation and the conditions that are in these disks. So what I showed you was some data from ground-based telescopes. It's challenging because you cannot observe for 24 hours straight. You get weather, you get sunlight, you have to stop, you're sharing the telescope with other people. So you tend to get kind of sparse time series. But the great thing is that within the past 5 years, we've literally had this revolution with space-based telescope photometry looking at young stars. And that actually kind of started with the Spitzer telescope, which is another NASA mission that operates in the infrared. And that looked at a number of young stars. And in the infrared, we're actually directly seeing the radiation from the the warm inner disk edge, which is a few hundred Kelvin in temperature. So Spitzer, over the past few years, has looked at a number of young star clusters and monitored the infrared brightness changes. Then there was Corot, which was a French space telescope mission that looked at a single area of the sky that had young stars in it, and that started to reveal some very interesting patterns in the brightness changes of these young stars. And now what I'm most excited about, because I'm working on it at NASA, is the K2 mission, which is the follow-on to Kepler. And that mission is able to look at many different regions on the sky that have stars that are anywhere from 1 to 10 million years old. And the great thing about all these missions is that they give amazing precision in their light curves, sub 1%, and they look continuously for months, several months at a time. And so you get really exquisite data. So we're going from previous light curves that look kind of like this. These are some examples of ground-based data. You can see these young stars are doing something, but kind of who knows what, to exquisite time series that look more like this with month-long time scales. You can really start to see the features and try to figure out what exactly they correspond to, what the physics is going on, how it relates to the inner region of these planet-forming disks. So over the past few years, we've observed enough young stars that we've actually been able to categorize their behavior and somewhat figure out what's going on. And so for the stars that have disks around them, 20% of them show this kind of quasi-periodic behavior, and we've seen it with K2 now. We saw it with Corot and Spitzer. It shows up in all the data sets. It's not perfectly repeating, so we don't think that it's cool spots on the star unless they're changing really rapidly. It may be hot spots on the star, or it could actually be something in the inner region of the disk that's encircling the star and creating this quasi-periodic pattern, but it's changing on day-to-day time scales as well. So that's one pattern that we see. We also see these upward flux events where the starlight is kind of undergoing these bursts, and we've seen that. There's also another telescope, a Canadian telescope called MOST, which has observed a few young stars. Seen it with that telescope. About 10 to 15% of the young stars show this kind of behavior. And the best explanation we have for that so far is that it has to do with the unsteady flow of material from the inner disk. So here we're looking at a very complicated theoretical model. The inner disk edge is sort of the outer part of these circles. The red lines are magnetic fields which go from the stellar surface to the inner disk, and they funnel material along them. And then you see how the models suggest that gas flows from the inner disk onto the stellar surface. And depending on whether that configuration is stable with sort of two funnels or unstable with lots of tongues of material, you can get different kinds of behavior at the stellar surface. And this is relevant to planet formation because, the flow of material onto the central star also affects the dynamics of what the building blocks are available for the planets themselves in this terrestrial planet zone. And it also may affect whether planets themselves fall into the central star. And so that's one reason to understand better how we can link up these models to the observations. In about 20 to 25% of cases where we look at these young stars with disks, we don't see upward flux events. We see these dipping events. So we call these the dipper stars. And again, we've seen those with a variety of space telescopes now. And what we think they are is that we're looking right through the inner rim of the disk. This is a sort of profile view toward the star, and the inner rim is periodically, or maybe not periodically, occulting the star along our line of sight. And so every time material goes by, it's not a planet transit, but it's like some kind of dust cloud, we see these dips. And they can be quite big. They can cause the brightness of the star to dip by 50% or even more. And so we have some models for that as well, and they suggest that these inner disks are not smooth axisymmetric structures, but they have bumps and warps in them. And what we think is that when the inclination of a disk is about 60 to 75 degrees is when we see this phenomenon. If it's exactly edge-on, then there's too much material to look through and we don't see the star at all. So typically, based on these observations, we think we're seeing warp-like structures in the inner disk, which may somehow affect planet formation, and they have scale heights of about 20 to 30%, but they seem to vary, again, on even timescales as short as a day. So there's a lot of dynamically active things going on in these regions. We can also use different filters with our data and look at how the color of the variations changes from one filter to the next, and we can compare that with looking through different types of dust, and different dust grain sizes will influence the color that we see of this behavior. And again, looking at the observations, this suggests that the dust in these regions is very different from the dust that's just out there in space in the interstellar medium. And that may be an indication that the dust has been processed and is starting to form planets. And again, these structures come and go on month-to-year timescales. So sometimes you look at a star and it's doing one thing, and then you come back a year later and it's doing something else. So it's a very dynamic region. One of the most exciting things is that some of these so-called dipper stars, about 20 to 30%, have very brief quasi-periodic fading events. And by brief, I mean like a day or less. You can see some examples here that we observe both with the Corot telescope and K2, and they're fairly regular, but as you can see, the depths of these dips are changing. So you wouldn't mistake it for a planet, because a planet would have a much more stable signature. And sometimes they come and go, and so there's something occulting these young stars, but it's not a planet. So the question is, could it be some kind of forming planet? Here's another example where we saw it with Spitzer. And so one thing that's been suggested is they're literally giant dust blobs, which may be the precursors to planets. But the interesting thing is, if you come up with a very simple model, and you assume that these events take place at around 1 day time scales, they induce about 20% dips in the star's flux, and maybe they repeat every few days. You can actually use a bit of basic physics coming to assume a size for the dust blob and a size for the host star. And what you actually get out is that the size of the dust blob has to be larger than the star itself. So these are not planets at all, and it's not even clear if you could get a dust blob that big. It probably wouldn't be gravitationally bound. So this model may not actually work. But the bottom line is there is something in the inner disks of these stars that's occulting them, and we think that that is somehow related to how planets form in these regions. There are some alternative models. For example, you could have the central star surrounded by a disk that has spiral density waves, which again may be seeding planets, and you can get sort of the rough pattern of these dips. The model here is shown in blue, and then some data is shown in gray, but you can see it doesn't really match the change in depth. So the jury is still out as to what these giant blob things, if that's what they are, and how exactly they connect to planet formation. So that's sort of where we are at looking at indirect signatures of how planets form in these disks. We're making progress, but clearly it's very complicated, and these regions are very dynamic, and we are awaiting more models to explain the data. But in the meantime, we're also looking for planets themselves with a variety of methods, but particularly with K2, to try to discover them right before or after the disk disperses in the very early stages to figure out how and where they formed. And there are several methods to do that. One is direct imaging, to actually take a picture of a disk and try to see a planet in it. Another is to use radial velocity monitoring to look at the wobble of the host star to see if a planet is tugging on it gravitationally. And then there's transit detection, which is challenging because if there's still, as I said earlier, dusty material in the disk, chances are the planet's forming in the disk. So if the planet transits, then the disk is edge on and you're looking through it and you may not see the planetary signature. But if we look right after the disk goes away, or if it's thin enough, we may have a chance of doing that. So this is an example of some of the direct imaging efforts that have been going on. I'm not personally involved in these, but in the past few years there have been some very interesting results. Very few, just isolated cases, but there is what's called aperture masking imaging. So the central star is blocked out, but what you're seeing is disk material, and then zooming in. This data was taken with the Keck telescope and the Large Binocular Telescope. There are these intriguing sets of blobs in the inner disk, about 10 AU or so from the central star. And it has been proposed that because this particular star system is about 2 million years old, that these are actually protoplanets in the act of formation. This is the only such image we have so far, and so we're not really sure yet what these blobs are. Are they somehow related to the blobs of material that we're inferring from time series? We don't know, but of course this is much further out. This is about 10 astronomical units, so it's not in the inner disk edge. If these are forming planets, they're forming quite a bit further out than the Earth is from the sun. And then another technique is also to take images of the disk itself and look for slightly more mature planets. And so there was a result that came out last year with a detection of a fairly young planet around the star Epsilon Eridani, and you can see that planet down here. But this is about 500 million years. So by some standards, this is actually a teenage star and not a really young one. And so things could have already happened that we're missing out on. And it's also about 10 astronomical units from its parent star. So it's not probing that interesting region where there are super Earths and hot Jupiters. We really can't do that with these techniques. So as you see, some progress is being made, but there are some limitations. Now, several months ago, there was an announcement of a possible planet around a 2 million-year-old star in the Taurus star formation region, detected with the radial velocity signature. And you can see some variations in the velocity of the central star, and it appears to be periodic, but more data does need to be collected. And the reason why the radial velocity technique does not work very well with young stars is because they are so active magnetically. They have spots on their surfaces, and those interfere with the velocity measurements. And so typically, while the older stars, where we have detected hundreds and thousands of planets with that method, we see a clear periodic signature as the planet orbits the central star. For the young stars, there's a lot of noise mixed in with that. And so in this particular case, the group reporting this possible young planet actually used some special techniques to do with spectral polarimetry to map the surface features of the star. You can see it in the corner, and then subtract that effect out from the radial velocity signature, and then infer that there might be a planet around this young star. So it's actually very difficult to use some of the same techniques that we've used to find planets around other stars to do it around the young stars. They're much harder. So what we have been focusing on mostly with K2 is to find transits of planets around young stars. And a few years ago, there was an announcement of a possible planet candidate around a star in the Orion region. And as you probably remember from seeing these data that I showed you earlier, there's a lot of stellar variation from various sources going on. And so it's actually hard to detect the little blip that a planet induces in the light curve. And so the folks that were observing this star somehow managed to detect this little blip here, and then there was all this other variation going on. But when they phased up the light curve, they thought maybe they were seeing the effect of a transit. Now, this has been kind of controversial because they've gone back later and not always seen the transit, and some other follow-up methods have been applied to this particular system, and the jury is really still out as to whether this little blip that's been seen is actually the influence of a planet or it's something else. So this one kind of remains a candidate. But as soon as the K2 mission started several years ago, we're very excited about looking for more possible candidates. And for those of you who are more familiar with the Kepler mission, you might wonder, well, why didn't we do this earlier? And the thing is, Kepler was great for finding planets, but it only looked at one region of the sky for 4 years, and there were no million-year-old stars in that region. So most of these young stars that I'm talking about, they're born in clusters, and they're still in those clusters at this point. And so Kepler looked out at this one region of sky, but there are all these star-forming regions in other parts that were completely missed, and those are where all the young stars lived. And so then along came the K2 mission, and K2, as you probably know, points in the plane of our solar system in the ecliptic, and there are young star-forming regions in the ecliptic. And not only that, but it looks about 80 days at a time at each region, and then it moves to another one. So we're not just looking at a single star-forming region, we're looking at different clusters, famous ones like the Pleiades. We're looking at star formation complexes where you still have a lot of nebulosity, such as the Rho Ophiuchus region. Looking at beehive clusters, older clusters, and numerous very young stars, several thousand to be exact. And the reason why K2 is so great is because it has a huge field of view, and that is something else that has hampered studies of young stars for a while. Typically, they span quite a big region on the sky, and so in order to get data on all the stars, you kind of have to pan around, but then that introduces gaps in your data. So K2 can look for 80 days straight at a 10-degree field of view, which might encompass several thousand young stars at a single time. And that's very important for building up statistics for planet detections. So initially, we looked at a couple of these young star-forming regions with K2, and as expected, these stars showed variability, some of which was kind of well-behaved, some of which was evolving over time. And some of these stars did show little blips that we thought might be transits. But the trick is, when you're looking in these star-forming regions, there are a lot of binary star systems, some of which are eclipsing each other. And the regions are also more crowded. And so when you look at one star, sometimes you don't actually know if there's another star or a pair of stars really close to it that's blended in with the light. So it turns out it's quite possible to get what's called a false positive, where you have two stars eclipsing each other blended with the light of a third star, and so it looks like a planetary transit, but it's actually just stars. So in fact, all of these cases which you see here, we thought they were promising, but it turned out there was no planet involved at all. So that was too bad. But then we hit the jackpot earlier this year. So we spent the second campaign of K2 looking at the Upper Scorpius region of young stars. These ones are about 5 to 10 million years old, which is kind of on the older range of the young stars. So they're about getting rid of their disk material, and it's much easier to see if there are planets there than the very young ones, which are still very heavily embedded in that dust and gas. So we looked at several thousand young stars in this Upper Scorpius region, which you can see imaged here. And it's fairly crowded, but we examined each star very carefully, and there was one interesting one in particular, which is now being called K233. And we got the data on this particular star, and it showed all this variability. So this is the star's brightness over time, and it's varying by only about 1%, but the data from K2 is so good that we resolve that variability quite well. And you can see a repeating pattern, which is probably a cool star spot on the surface. But if you look really carefully where all of those red lines are, you might make out a very little blip. So this is really hard to see, but you can imagine if you remove the signature of the higher amplitude variability, maybe these might be a planet, or maybe they might be something else. So this particular star was actually reported as a planet host candidate, I believe, last year, along with a number of other possible planets from the K2 mission by Andrew Vanderberg, who is based at Harvard. And he just had a table in his paper of all these stars might have planets around them. But what he didn't realize was that this was actually a baby star and maybe a baby planet system or baby planet around it. And so a group that I was working with, as well as another group, looked a little closer at this light curve and realized, aha, this is in a star-forming region. This could be a very interesting object if it's actually a planet. So we looked at the light curve, we phased it up, and that is the overall variability you're seeing, which is probably reflective of the rotation period of the planet, which is about 6 days. But again, you see some little blips. There's one here, but they're clearly not lined up with the rotation period of the star itself. So when you remove this signature of the rotation and then you phase it up to a different period, you start to see all these periodic transit-looking effects. And then when you phase it up to just over 5 days, at about the 0.2% level, you see something that looks like a transit. So the question, of course, was, is this a planet, or are we being duped again, and it's just some stars that are eclipsing each other and there's another star close by? So we had to do a lot of work to rule out the alternative scenarios. And one way to do that is to measure the radial velocities of the central star, and if there's a star-sized object orbiting it, then you will see the central star wobbling like crazy. But as you can see from this data, this is the radial velocities phased over the period of that possible transit signature, and the error bars are small enough that it really can't be a stellar companion around this object. You can see two models overplotted. One is about 1 Jupiter mass and one is 4 Jupiter mass, and even the 4 Jupiter mass companion would have induced a much larger signature. So we can already start to rule out a variety of scenarios involving larger non-planetary companions. We also did a lot of follow-up high-resolution imaging using techniques such as adaptive optics, looking in the infrared, and then also taking a spectrum of the star. If there's 2 stars, you might see the signature of the second one show up in the spectrum. And again, nothing. So in the end, we were basically able to come up with these diagrams that show all of the regions of parameter space in terms of star-planet or star-star separation and difference in brightness between the star and the companion, and pretty much rule out everything except for this little gray region in here. So we're not 100% sure this is a planet, but most of the scenarios we can think of, even in this gray region, do involve a planet. And so the probability that it's not a planet is something like less than 10 to the minus 6 or even 10 to the minus 11. So this is now basically a confirmed planet around a young star, statistically speaking. So that's really exciting. It's about 5 to 10 million years old. The star itself is about a third the mass of the sun, about the same size as the sun. Its brightness, if you like to think in magnitudes, is about 14th magnitude, which is a bit faint for an amateur telescope, but quite bright for the K2 mission. It's also not that far away. It's about 150 parsecs or 480 light years, and that's about as close as you can go and find young stars. We don't have that many young stars in our nearest neighborhood. So for those of you that heard the talk last week about Proxima Centauri, that's a possible planet that's really close to us. We're not going to find any young forming planets that close because there just don't exist any young stars. So this planet is orbiting at a period of about 5 days. That makes the semi-major axis, the distance from the star to the planet, to be about 4% of the Earth-Sun distance in AU. So it's really close to its parent star. It's about 5 or 6 Earth radii, so it's a little bigger than Neptune in mass. And we can put a limit based on these observations. It's definitely less than 3.6 Jupiter masses, but it's probably way less than that. There is some remnant protoplanetary disk material around this star, which tells us that, yes, this is a young system. And so interestingly, the inner edge of that disk is about 0.2 AU from the central star. So this object is orbiting within the inner disk region. It's not actually in the disk. It's in a cleared out central region. And that dust in the disk is only about 120 degrees Kelvin. So here's kind of a depiction of the system compared to our own solar system, our inner solar system. And you can see there's Mercury, and then here's K233b, the planet. It's way in there, really close in. And this is, of course, an artist's conception. It's probably the type of planet that you might call a hot roaster. So you can think about whether there would be any life forming there, but I have my doubts. So this is really interesting, because how did that get there? You know, we found plenty of planets with Kepler and other missions that are around middle-aged stars, and that are that close in. And a lot of folks who come up with planet formation theories thought they can't possibly form that close in. They have to form further out, and then they have to dynamically migrate in. But this thing is only a couple million years old, and it's already in there. So there's kind of 3 scenarios that have been under consideration. One of them is like scattering between bodies in the disk, and that changes the eccentricity of the orbits of planets, and it also can push them way inward. But that is essentially ruled out by this system because of the orbital period of the planet and the star, and the fact that it's probably pretty circular. Another idea is that it did form further out, and it just moved inward really fast, like faster than any of the theoretical scenarios so far have predicted. It's possible, but again, the big question is, well, if the planet formed further out and moved in really quickly, why did it stop and park where it is now? So that's kind of a mystery for people to explore. Or maybe it did form right there, but there's an issue of how it actually got enough material, because there's actually not a whole lot of dust and gas in the inner disk to form a Neptune-sized planet. But maybe it's possible. So there are kind of 2 scenarios. We don't know which one is the case. We need to investigate more, maybe look for other younger planets. Will we find more? Possibly. So K2 will look at this Upper Scorpius region again in 2017, but it's actually not going to revisit this system. It's going to look at kind of more of a corner of the region that we looked at before. So it won't look at quite so many stars. But it recently observed additional young stars in the Lagoon Nebula, which is a couple million years old. And then next spring, it will look at the Taurus star formation region, which is also a few million years old. So there are more opportunities to find transiting planets. But as you've seen, it's challenging because you have all this other variability to contend with and to remove before you see the signature of a little planet. And also, we are kind of talking about low number statistics compared to the number of stars that we observed with the Kepler mission and are now looking at the K2 mission is much larger than the number of young stars that we have access to. So it's actually not surprising that we've only found one so far. That's kind of in line with our expectations, but we hope we get lucky and find more. And then on the slightly longer timescale horizon, there is TESS, the Transiting Exoplanet Survey Satellite, and that's going to observe almost the whole sky in different sectors, 27 days at a time, at a 30-minute cadence, and it'll cover almost the entire sky in a couple years. And this might help with looking for the more dispersed and massive young star regions. It could find some transiting planets. We'll see. So to conclude, I've showed you the two main observational approaches that we're pursuing to investigate planet formation. The first is to look for these indirect signatures of forming bodies in the protoplanetary disks. And it's very hard to see into those inner regions where there may be terrestrial planets forming. But the time series photometry is showing us that there's very interesting structure there. It's not just a smooth distribution of materials. Stuff is already clumping up at a few million years old. And there are these azimuthal asymmetries and warps, and they're changing on pretty short time scales. And then when we look through the dust to the central star with these obscuration events, we can study the properties of some of that dust, and we can tell that it's evolved away from the dust that's out in the interstellar medium. And then, as I just showed you, we're starting to discover planets or protoplanets themselves right around the time that the disk is going away. Several young planet candidates. I just showed you K233b, which is our first fully formed newborn exoplanet. And hopefully with the future, with tests and also advances in interferometric imaging, we might be able to see some more planets more directly. So thank you.
Okay, we have plenty of time for questions. It works as you stick up your hand and I run around with the microphone.
Okay, there was recently in the news, in the last few months, a star that had some extreme variability, and they are proposing maybe even a Dyson sphere was being constructed around it. Got in the news.
Yep.
Do any of this stuff, interplanetary dust disks,
Yep.
possibly explain that star?
Well, to be honest, it actually makes me skeptical about that star because I'm so used to getting this young star data and seeing really bizarre things. As you probably saw today, there's all these dips in their light curves, there's bursts, etc. The confusing thing about this star that has been in the news is that when we look at it, we don't detect any dust at all around it. So for the stars that I was highlighting today, when we use infrared facilities like Spitzer, we see an infrared excess emission, which tells us, yes, there is some warm dust around these systems. And that warm dust is a very good explanation for what we're seeing in the young stars. For this other star, it's like a middle-aged system. So if there is dust around it, A, we can't see it, and B, we don't know why it would still be there. So that makes it a little more mysterious. But again, as I said, I'm so used to seeing strange things that when I saw this other star, I was like, oh, it's just another strange thing. There's some explanation, we just don't know what it is yet. Swarms of comets. Possibly. I mean, it could be that there are fully formed bodies from planet down to smaller size and that they're breaking up. There are some problems with that theory, but so it does kind of resemble the young planet systems, but figuring out where the dust came from is quite challenging. Yeah.
How does the activity of a very young star with solar star winds blowing out material from the disk, how does that figure into the models?
Well, so there's basically material going in from the inner disk, hitting the star, and that creates these bursts that we saw in the light curves. There's also outflows in some cases where there's jets of materials coming off the star. I don't think that affects the photometry so much, but in terms of the models, it's actually quite complicated and difficult to model the inner disk region and its connections to the star. It requires like 3-dimensional magnetohydrodynamic modeling, which is really expensive in terms of computer time. So what we have in terms of the models right now is really limited. It's kind of the observations are leading the way and saying, hey, there's all this interesting stuff going on, but we haven't figured out exactly what it all is yet. Mm-hmm.
Hi. You mentioned that disk-driven migration is hard to explain because the question is, it must have been rapid. Mm-hmm. How did it stop? The question I have is, how do you know it stopped?
Yeah, that is a good question. I was wondering myself. I don't know if you could tell on the short time scales of the K2 observations. So I suppose it's possible. It's not the planet is not so close in that it's, it itself is evaporating. We have seen that in a few cases. I suspect, we'd have to revisit this system and kind of see how stable the orbital period is. But yeah, I'm not sure. I suppose it could be moving in. There may be a reason why we know it's not, though.
Hi, Anne-Marie. So for the younger the star is, on average, the bigger the disk, the more stuff you see going on in the light curve. So what's the youngest star around which you can hope to find a planet by the transit method?
Well, it's roughly a function of age, how much disk material's in there. It's kind of like an exponential decrease. But even if you look at one star-forming region where you think all the stars are the same age, some have disks and some don't. So you can't really attach a particular age and say, the target, these stars, we can see planets and these don't. The candidate that I showed earlier that's controversial, that's about 3 million years old. So I suspect that's probably about the limit, but it's definitely easier once you get beyond 5 million years or so. But it could also be that eventually we get better at decomposing the different components of a light curve, so we can somehow take out the more chaotic pattern and then see a transit that's left over. That's, again, something that we're actively working on.
I'd like to ask a question about the distance of the planet from a star. You say it seems unlikely that it could have migrated in that rapidly. Some of the theories indicated that migration for a sufficiently thick disk could occur in a few orbital periods. So you're talking about, weeks, months, years at most. And so that might explain that. I don't know whether that theory is still appropriate for your example here. And of course, the other thing they talk about is if the star is rotating more rapidly than planet is orbiting, that will stop the planet from coming in. Although I think what you showed was the opposite was true.
Yep.
Which case the star would be bringing the planet in.
Yeah, that could be. I mean, obviously, most of these migration theories have been based on started with the solar system, and then they expanded a bit once hot Jupiters and other close-in planets have been found. But every new system like this that we discover, causes a modification. So it's entirely possible that there is really rapid migration and that there is a way to explain it.
Thank you. What is limiting current investigation of planet formation in terms of technology, tools, and so if you had more funds, what would you do?
Well, it depends on what region you want to look in. I think it's definitely easy to look into the sort of 10 astronomical units and beyond, but I'm really interested in the close-in regions, and for that, we need multiple big telescopes working together as an interferometer to get really high spatial resolution, probably at infrared wavelengths where you get the best contrast between the star and the planet. So that's something I would like to see happen, and there are some sort of conceptual plans for such instruments in the future, but some of them, they probably won't actually happen until the 30-meter telescopes come online. So some of the technology is in development for that, but it's partly very expensive, and there's a lot of other priorities that involve techniques that are probably focusing on the older stars. So, but getting bigger and more sophisticated interferometers is one thing that I'm very excited about. And also to look at these stars with the disks and actually resolve the inner disk region and see the planets in there. It's something that could happen, but it's kind of like 15 years off.
Was there anybody else who had a question? Okay. We have, of course, the traditional thank you for all speakers at the SETI Colloquium.
Thank you.
And we thank Anne-Marie again.